All right, I guess we'll go ahead and get started. Again, I'd like to thank everyone for being here today. I'm Heather Brooke. I'm the Chief Chemometrician at Camo Software. Looks like I see a couple of familiar names on here who've come to some of my other webinars, so thanks for that. Today we're going to talk a little bit more in depth about partial least squares regression and some of the techniques for using it and doing some pre-processing, which tends to be one of the big questions on how to handle your data. So feel free to ask any questions in the panel here during the seminar, and if I don't get to them right away, I'll definitely have a question and answer session at the end, so have those ready to go. All right, so just a quick overview about what partial least squares regression is. Again, we remember that this is a situation where we do basically a PCA of our X data, get our scores from that. That's going to be your T1. And then you do a PCA of your Y data as well, and that's going to be your U1. Take the scores of that, and then we plot them against each other so that we see the covariance between X and Y. So it basically forces the looking at the variance in X that most explains the variance in Y. So when we're in the partial least squares arena, when we have the components, they're not called principal components like they are in some of our other analyses, but they're called factors. And the reason why we call them factors is that it's because the factors are directed by the Y data, so they are connected very significantly to your Y data. I'm saying people can't hear me. All right, I think I'm showing that my microphone is working fine, so if anyone else can confirm that they can hear, that would be great. All right, I'm going to push ahead. So one of the things we look at when we are doing our PLS analysis, one of the first things we look at is our loadings. And in this case, we have our correlation loadings. And what that does is that takes a look at how the X data and the Y data work together to explain the data here, right? So one thing that's nice is that when we have our loadings and then our loading weights, if they are similar, then we can interpret the X and Y structure well. And that means that we've done our pre-processing correctly. So when we look at our loadings, the loadings themselves are going to be the variance in X, the most variance in X. The loading weights are when it's how they're weighted towards the Y. So if they look the same, you're showing that your variance in X is very much related to your variance in Y. And when you do your correlations loading, it puts them on the same scale so that you can see where the structure and the unmodeled structure is, right? So in this case, if we're looking at our correlations loading, if we're looking at our percentages down here, what we see here is that 91% of our X variation is explaining 47% of our Y variation. And that's pretty good in this case. We're looking at some P data here and how flavorful they are based on their chemical makeup. And so what we're seeing here is that we've got some highly correlated data here. So we've got some variables here that are strongly influencing how sweet and how good flavored things are. And then over here we have our variables that are saying how off flavor and how poorly tasting they are. This is another look. So this is looking at our loading weights. And you can tell that this looks like a very similar plot to our correlation loadings, which means that these are definitely the most important variables for predicting the good taste. These are the most important variables for predicting the bad tastes. And in the center here, we have very low y-explained variance in principal component 2, and these are very close to the center here, so they are not affecting your data very much. If we look on the side, we're showing about 3% of that X data variation is explaining only 9% of the Y variation. So in this case, we're looking at basically a one-factor model. So a lot of us use spectroscopic data. So I'm going to show how you look at your spectroscopic loadings as well. In this case, we're looking at a number of fuels that have different octane levels, and some of them have an additive to them, which would be ethanol. And so what we see here in our X loadings, so this is showing us the most variation in X. And as we see, we have a couple of samples here that are different than the rest of the population. And because these loadings are showing up, this is factor 1, and that's the direction that these factors are in. That's saying that this is highly correlated to what's separating these samples from the other data. If you ever see your data and your scores start to kind of line up mostly along factor 2, that's telling you that there may be some extreme samples or some outlier samples that you might want to deal with before you move on in your analysis. If we remove those two samples, as we can see here, now factor 1 is explaining 85% of our Y data as opposed to the 41% of our Y data in the previous system. And now our scores are evenly distributed across both factor 1 and factor 2. And we're getting over 90% of the variation in Y explained here. Now, if we want to look at our X loadings versus our X loading weights, remember the X loadings here are the regions that are most variation in the X data, and the X loadings are the regions in X that are most related in predicting Y. What you really want is for these to look similar to each other. If they look similar to each other, then that's telling you that you've done your pre-processing well. So here's where we remove those outlying samples, and now we see that factor 1, our variation in X, looks very similar to the variation in X that predicts Y. So that's just a way to kind of analyze your data. Another good thing to look at when you've done your PLS modeling is what we call XY relationship outliers. So there's lots of different types of outliers, and I think the last time we talked a little bit about the ones that are spectroscopically different from each other, ones that and those are with the high residuals, and we have some that are within the model, but they're just extreme samples. Maybe they're on the edges of your range that you were predicting. But sometimes we don't see the outliers until we look at how the X and Y relate to each other. And that's what this does. So this takes our plot of actually the U scores, which is the Y scores, versus your T scores, which are your X scores. And you can see where some outliers might be. And you can see in factor 1 here, these are very clearly not on a nice one-to-one line like you would want to see. When you get to factor 2, now we are predicting a little bit better. We're seeing a nice correlation between the X and Y, and the same thing in factor 3. Once we get to factor 4, you see this starts to look like a shotgun effect. You don't see very much correlation between the Y output and the X variation. And so that's another way to help you determine how many factors you want to use in your model. And you can get these plots by when you're in your unscrambler. You right-click in any of your plots and you go under XY relation outliers. And I always do the quad plot because that shows you your first 4 factors all together. Makes it a little bit easier to see what the trends are looking like. So another thing you want to look at is your B coefficients in your regression model. So now this is the basically the equation that is going to multiply your original spectra by so that you can get your new output. And so each point is a weighting factor applied to your X data in order to predict your response. If you're looking at process data or sensory data, you like to look at these in bar plots like this so you can see the individual samples. And then for your spectroscopic data, you would get these regression coefficients, and it should look like a spectrum. If this starts to look really noisy, then you might want to dial back to less factors. Okay, and this is what is applied to your new X data to be able to predict your unknown responses. One of the things we provide in the unscrambler is something called uncertainty testing of these regression coefficients. Basically, that looks at your main model and your submodel divided by the number of segments, and it looks at how your individual variables are changing in respect to the Y structure, right? So if we zoom in here, you can see that there are certain plots, certain areas here that while it's generally a positive trend, our statistical limits of how it's varying, basically our standard deviations, are crossing over 0. So that's saying that sometimes as Y is increasing, then that X factor is increasing, and sometimes it's decreasing. So it's not modeling the Y structure very well. So it gives you a way of being able to narrow down the variables that you want to use, because you only want to use your X variables that are describing Y well. And it will automatically highlight those for you, so the ones with the cross hashes in it are considered important variables for predicting Y. And then you can go back and do a redo your analysis only using those factors. This is just another example of when we're looking at something like sensory data. It's maybe a little bit clearer. You can see where the variables are crossing 0 and where they're not. It also helps you see which ones are contributing more than others. So the further away from that 0 point it is, the more highly it is explaining your Y data. So sometimes, in this case, this is where you might see that something has a weighted regression coefficient that is not explaining things very well, but then when you look at your regression coefficient that you're actually going to be using, it has a very high value. So that's kind of another indication that you need to remove those variables before you move on. Here is an important variable, right, that has a very low B coefficient. So it helps you narrow in and look at what are actually important and what's not and how you want to move forward. This one here is going to be your most important variable because it's highly important and it has a high regression coefficient. So one of the biggest, most often questions I am asked is, how do I pre-process my data? So I'm going to talk to you a little bit about that. There is no direct answer to this. There are some approaches to determining how you're going to do pre-processing, but there's no real rules of thumb to say if I'm using NAR data, I'm going to want to do X, Y, and Z. You really have to know your analysis and look at the variations that are happening in order to determine how you're going to do your pre-processing. So one of the great ways to do that is in our software, there's something where you call descriptive statistics on spectra. And this is under the Tasks and Analyze folder. So what this will do is show you which spectral regions have the highest variation, and you can determine whether this is due to sampling or chemistry or whether there's any scattering effects. So what you get when, let me go back, sorry. This is basically a box plot, a quantiles plot, and so you can see which areas are changing a lot. That's going to show your min, your max, and then your median and your quartiles. And so you can see in this case, it's down up here, these regions are the ones that are varying quite a lot. And this is that octane data again. So those are the areas that had the samples that had some additive in them. Now what we can do is if you right-click in here, and I'll show an example of this in a minute, there is a plot called scatter effects. If you do that and then look at all of your spectra together, what you can see is what's happening with your data. If you see some changes like this, that's kind of showing, or some swirls, that's saying that there's some chemical changes that are happening to your data. If you see that they all look very similar and have the same slope, but there's just an offset, then that's a particular type of scattering effect. And I will show some more of that in some later slides. This is another way you can look at on your constituents. So this is going to show you your original variables in, say, a sensory data or a process data situation. And what you see is something like purity here has a very high number and varies a reasonable amount, where something like impurity has a very low absolute value and a very small amount of effect. So what you want to do then is, this tells you that you're definitely going to need to mean center and scale your data so that these variables of purity aren't considered important just because they happen to be a high number. And so this is here when we centered and scaled our variables. And you can do some sample grouping with this as well. So we can look at what the whole range is for all the samples together and what they are with the high, low, and medium. So you can see that some of these are changing a lot depending on which level of octane is in these samples. So here's an example of when you're seeing additive base shifts. This is what your line plot will look like. You'll basically just see a general baseline shift. And in our scatter plot with the descriptive statistics, you would see something that looks similar like this. All of your samples are going to have a similar slope, and they're just going to be at a y offset from each other. And that's just saying that there's some effects that are happening that are consistent across all the wavelengths. We also have multiplicative effects. These come into the case where you have, for example, different particle sizes. So you've got scattering that's changing dependent on the wavelength and particle size ratio. So you're having less scattering down in these areas and more scattering in these areas. And that's why we see this fanning of the data. And that fanning is a very telltale sign that you have multiplicative effects, which means that the scatter is different dependent on the wavelength. So in the unscrambler, we have all kinds of ways to pre-treat our data. We know from a lot of times you just cannot use raw spectra or your straight process variables. So we have lots of very spectroscopic type pre-processing and smoothings, derivatives, things like that. And keep in mind in the unscrambler, when you do a pre-treatment, it creates a new matrix for you to work in, and it associates that pre-treatment with that matrix. So if then you run a model on that, it will automatically apply that pre-treatment to new samples. So you always want to make sure that when you do predictions, you use your raw data when you go forward. So there are different types of transforms. Some are column-oriented. That means that each variable is scaled individually through the samples, right? So spectral data can be down-weighted different wavelengths that have no information or little information. For non-spectral data, this are data that's measured in different units. Auto-scaling is very common, so mean center and division by the standard deviation. And then there's also row-oriented. So this is where each individual sample is transformed on their own. So this might be an alignment of a spectral peak. This may be removal of your additive and baseline or scattering effects, interpolations across your wavelength, so doing a derivative, that's going to be row-oriented. And it's very important to know which types of transforms are used in which way so that you can apply them appropriately. Now I talked about additive and multiplicative effects. This is a nice little chart that I use a lot so that I can keep track of which types of transforms correct for different types of effects. All right, so now I'm going to show an example in the unscrambler and how I would go through and do stepwise sort of my analysis on deciding which pre-processing methods I want to use. So I've got the unscrambler here. Great, looks like that's up here. Now what we have here is some spectra that were taken on mixtures that were made of gluten and starch. So we've got ranges from 0 to 100% of starch and vice versa in gluten. Now in this case, we know that because if you know what starch is, you know what gluten is, this should only be a one-factor model because you only are predicting one the difference between two things, right? So what we always do is I like to run a model just on the raw data to see where we are starting. So I'm going to go under Tasks, Analyze, PLS. I have some reference data, so that's going to be my calibration set data, spectra, and we want to predict gluten. I'm going to bump this up just because it's, no, we're going to do that 7. Ooh. We're going to say OK. So this is what we see. In this case, the unscrambler will give you a suggested number of factors by looking at your explained variance and maximizing that and minimizing your error, right? But remember, so in this case, it says that we need a 3-factor model to really explain all of the Y variance. But as I said, we know that we only should need one factor in this particular case. So if we bring this back to factor 1, we can see that there's still a lot of variation that's happening here, right? And if we look at factor here, we're showing that we're only using 42% of our X data to explain 74% of our Y data. So that's not really good in this case because we are expecting a very clear separation of the two. I'm just going to rename this so we can keep track that this is the raw data. Now what I'm going to do is from this I can see I definitely need to do some pre-processing. If we right-click in here, we can do some sample grouping. Under here I'm going to look at gluten, and we can create row sets based on 5 groups because we know we have 5 different levels here. I'm going to highlight these and pull them over. And with the legend, we can see there is a general trend in this data, but what we'd really like to see are these points right on top of each other, right? So that we can use as few factors as possible. So what I'm going to do now is under Tasks, Analyze Descriptive Statistics. I'm going to look at my reference data and the spectra. And these are those quartile plots, quantile plots that I was discussing earlier. What we do here is we right-click under Statistics, and there's Scatter Effects. And what this is showing is each data point of one spectrum plotted versus the mean of all the samples at that same data point. This is just looking at one spectrum right now, but what I'm going to do is take a look at all of them together. Now, what we can see very clearly, I believe, is that they all seem to have a general similar slope, but there's just this offset in the y. So that tells me I want to do an additive pre-processing treatment first. What I tend to do is I start with derivatives because what that does is highlight your peaks of interest, and it should separate them out a little bit. So we're going to go here, tasks, transform, derivative. I'm going to do all spectra. I'm going to do a second derivative. Now we can preview the results. So what this does is it allows you to see what your spectral changes are going to look like. Let me change this to our reference samples. And this shows you your raw data and then your pre-processed data. And the reason why you might want to do that is to choose the number of smoothing points you want to do. This still looks pretty noisy, say in these areas, so I would bump this up. And you kind of play around with this until it looks like something that it is enhancing your signal and reducing your noise. And I have shown myself that 7. 7's usually where I start, depending on how what the resolution of your data is. And so this looks like nice, smooth peaks now as compared to this. Now what you can do is you can over smooth. I'm just going to show you if I did 20 points. We basically lose all of our information in that case. So that's one reason why it's good to look at your preview as you're going forward. Okay. Now I'm going to analyze the PLS with that. Our reference spectra and gluten. This is just a warning to tell me that we've got some 0 points. That's going to be the ends of those, the derivatives, because you've got some smoothing. It doesn't actually start creating new points until number 7. So that's all that is. It's a warning. So you just say move forward and yes. Now this is looking a little better, right? Our first factor, 94% of our X data is explaining 94% of our Y data. So now in 2, we're still suggesting 3 factors, but we want to bump this back to 1 because we know it should be a 1-factor model. And in this case, it looks like it's explaining the very high values, but not the low values very well. We can compare our RMSEs to on the raw, and you can see there's pretty significantly better, and the R-squared is also better. We've got it over 90. But there's still a lot of structure that's not explained. We can see a lot of variance here in factor 2 that we don't think should be there. I'm going to rename this as well. This is second derivative. So again, this tells me that I haven't gotten rid of all of the noise, so I may want to do some more pre-processing. So I'm going to go in here, and again, I'm going to do these descriptive statistics. Take a look at those. And you can see the chemical structure. Things are changing kind of in these areas the most. So that's just something to look at. We're going to do scatter effects. Now we've got a lot of chemistry going on, even more so than the first time. And I'm going to do all. Now we can see there's that multiplicative scattering effect that I was mentioning. So that means there's a wavelength dependency here of scattering. So I'm going to want to do some multiplicative type work on here. So what I am going to do now is just from my experience, and this is the thing, you want to play around and try different things. That chart I can make available for you as a quick reference. But SNV is a pretty standard one that you would use with near-infrared spectra. So that's the one I'm going to apply, and I'm going to make sure that I highlight the one where we've already done the second derivative. Now we're going to transform that with an SNV over all of our spectra. Say OK. And let's take a look at that plot. So here we can do a line plot. We want to look at our reference spectra. And look at that. We've got some really clear differences in our data. If I go back for just a second to plot where we only did the derivative, you can see there's still a lot of overlap. Again, we can group these with sample grouping and take a look at the areas where the changes are happening. And you can see in certain areas, like here, maybe you're getting some real definition between the different groups, but then there's an overlap in this area. We've got some peak shifting, so it's some things to look at, right? If we go back here, let's take a look at the grouping here. Oops. Now you can see there's some clear shape differences between each of the levels of gluten here. And this is what you really want to see in your spectra before you start looking at your PLS. So now let's do our PLS. And right away we see we are capturing everything, almost everything in that very first factor. And it's using that full X range. So that means that we don't have any unimportant variables that are in there. It's saying that we're using all of X to explain almost all of Y, which is really great. And look at this beautiful predictive versus reference line. So if we put on our target line, so that would be a 1-to-1. There is this little bowing in here, but the prediction value is really good. So you're like 3%. You're within 3% of what you would expect to see. Really great R-squares, 0.99, beautiful slopes, and very little offset. And we can see here in our scores now, we've got these nice little tight groupings, which is really ideal in this case, because again, we have just a mixture of two things in this case, all right? So that's just an example of how I would walk through my data and do some analyses and figure out which way I want to do my pre-processings. Often you'll do more than one pre-processing and you'll lump them together. And this is an interesting case because typically you would do your multiplicative effects before you do your additive effects. But if you go in and the descriptive statistics, look at your scatter plots, that really gives you some justification of why to apply which things in which direction. Because typically people might have said that you would do an SNV before you do your derivatives, but it really depends on your case. And you really just can't get a better output than that. So I'm going to go back to my slides. So once you have a model, you can very easily apply that to new data, right? So you do your stage 1, your calibration, you deal with any outliers you might have, you refine, you validate, and then you do your prediction. So you do a prediction first on a test set, so things that you know what the Y reference is, just to make sure. That's the proof in the pudding. If your calibration might look beautiful because it's you have a very narrow set of data, but then if you get new data, if it looks different and it doesn't predict well, then you don't have a very robust model. So it's very important that you do sort of a test prediction set just to make sure that your model is valid. In the unscrambler, the prediction is very straightforward once the model's built. All the parameters are defined within the model. Like I said, it automatically applies your transformations, the same number of components, the same dimension. It'll also give you some statistics about how similar your new samples are to your original calibration samples, so you can determine whether you trust that prediction or not. You still have to look for your outliers. Every time you run an analysis, you've got to make sure and look for these outliers and make sure that the samples are similar. Use your outlier tools. That's going to be your leverage, your Hotelling t-squared, your residuals, to see if there's any outliers here. Again, this is just how outliers are kind of defined. So if they're similar, it's reliable. If it's dissimilar, they're going to be unreliable. So you can have something with a high residual, so that says that the spectroscopically it's different from the other samples, or by your variables it's different. If something is very far away from the center, it's still in the plane, so it's spectroscopically similar, as the same shape overall, but it's an extreme sample, like it's much higher in certain values than others, then it's going to be far away from the center of this data. Now, if you have something that's both high leverage, so very far away, and a high residual, so it's way out in no man's land here, that's a clear indication that you have an outlier. This is what the unscrambler shows you when you look at your prediction. You can get your predicted Y versus your Y reference if you have it. It'll give you a nice line. You can check your statistics here, and you want to compare that to your RMSE of calibration, and that you want to be fairly similar to each other. And the closer they are together, the more accurate your prediction actually is. This is going to be your predicted values. That's the center line here. And then the blue box shows how confident you are in your data, right? So something like this particular sample is very similar to your calibration data, so you're very confident in this one. In this particular case, you've got a larger deviation, larger room for error, so it's not quite as similar. It doesn't mean the prediction is wrong or incorrect. It just means you're not as confident in that. This is how we calculate that deviation in prediction. So you have your residual Y variance from your validated residual. You've got your sample variance, so that's your X validation variance that comes from the prediction of the new sample. Divide that by your average residual of the model from your calibration. The leverage of your new sample, and you've got 1 over the number of calibration samples they are, so that's going to be your degrees of freedom, essentially. And then your alpha is the number of factors. Again, that's another degree of freedom term. And so the square root of all this, that's going to give you what your confidence limits are. This is what you're going to see in your plot. You look at your inlier distance, so that's how similar spectroscopically your data is, what the residuals are kind of basically, and then your Hotelling t-squared, that's how far from the center of the model it is. So anything that is down in between these red lines is a good sample, and you can feel confident in your results. If you have something that's up in this upper right-hand quadrant or in the upper left-hand quadrant or the lower right-hand quadrant, those are your samples that you're kind of unsure of. You might want to take a closer look at those. You might want to say, hey, those need to be included in my calibration data. So that's another thing. When you have a model, your models are not static entities. They are dynamic. You always need to keep checking in and make sure that they're valid, that there's no shift in your system. If you change spectrometers, for example, sometimes that will change the output of your new samples, so you want to include new samples in there. And that's where you start to see, you look at these, and that helps you determine that. If you have anything that's up here in this upper right-hand quadrant, those are outliers. So those are ones you want to be concerned about. And you might want to do your traditional testing on them, for example. So again, this is just a prediction with the deviation. We're looking here again at that octane data, and we see our prediction data. We've got a number of samples that are very well predicted. We're very confident in them. But then we have these last four that have these very wide confidence intervals. And I know, because I know this data, these particular samples are the ones that had that additive in them as well. So once we took the model and used the one where it didn't include the additive samples, that shows you you can find those very easily. And depending on what you want to do, you might include those data and you might not. So if you want a sample that will tell you, or a model that will say, hey, I have something that has this additive in it, you might leave it like this so you can see that there's a difference. If all you care about is the octane level and you want to make sure that it's predicting well, you might include that in, or you might cut that area out because that particular those variables are changing with the additive rather than the actual octane level. This is just describing a little bit more. So our INLIER statistics, it's for detecting particular outliers during your prediction or classification. If your sample lies far from the nearest calibration in the score plot, then it's flagged as an INLIER. So it's basically this INLIER distance is how far away is your new sample from the samples in your original space. And the further away it is, the higher up on this scale it's going to be. So this happens, again, when your model's built on different grades of quality, or if your samples are from different raw materials are included in the model. So they also might be outside that Hotelling t-squared limit. So that's how far from the center of the model it is. It's not worried about how close it is to the other samples. It's like how far it is from the center of the model itself. So this is just explaining again. We're looking at this nearest neighbor outlier, right? So we have our, the red samples are going to be your calibration data, and what you see is you find the two samples that have the maximum or minimum distance away from each other in your calibration sample, and then if there are new predicted data that are further than that distance away, then that's that outlier distance or the INLIER distance. Something that is far from the center of the model itself, way out here, those are your outliers. So that's the difference between the two terms. So here's your INLIER critical value. So anything that's high in this area, those are going to be your INLIERs, something you want to look at. Maybe you want to include into your data set and redo your calibration to make it more robust, more accurate. And then your outliers are the ones that are very far, have a high INLIER value and a high Hotelling t-squared value. And so that's all the slides that I have for you today. If there's any questions, I would be happy to take them now. Right. So the question is, in this example, I knew that the sample is a single factor, but if there's a case where I don't know how many factors it should be, how do you determine what type of pretreatment? So the way to determine the pretreatment is actually the same. You would still do those descriptive statistics, look at your scattering plots, look at your raw data, see if there's any areas that stand out to you as well, so that might help you with some variable selection. The reason that I say that I knew that this was a one-factor model is because it was a mixture, right? So determining the number of factors, you want to know what you're looking at, know what your sample is. You should be able to have a decent understanding of how many things should be changing. And so you can use like the number of factors of the things you're expecting to change plus 1 is kind of a rule of thumb. Typically, I start to get nervous if I need more than 4 or 5 factors. But if you're doing something like environmental samples, there's so much going on with your soil and your the rain and the different nutrients. And in those cases, you might have more factors than that. So it really depends on your problem. I am recording this webinar, so you will be able to download this after and listen to it again. We don't give you the slides directly, but you can get and listen through this again. If I wanted to use a PLS model to simulate a Y by changing one particular X value, could I change all the values of correlated X's? I would say I've never done something like that, but my understanding would be yes, because if you do a PLS model and you see that, this range is changing significantly and say this range is changing significantly, then yes, if you want to simulate the change, you want to change everything that's going to be changing. Maybe you might also want to see the robustness of your model if you're doing a simulation by not changing all the correlated X's to see how much those particular areas affect your output as well. That would be an interesting way to look at that. Any other questions? All right, I think that is everything for now. Oh, wait, here we go. In a spectra like LIBS, where you have 9 to 10 elements are present in the spectra for emission spectroscopy, how to select the pretreatment? Again, you want to go through, you want to look at your data. One thing I do, I don't have a lot of experience in LIBS spectra, I'll tell you that now, but again, you look at those scattering effects, look at how things are changing. You want to see, I'm guessing if you're talking about only 9 to 10 elements are changing, I would look at auto-scaling, doing some mean centering, just to make sure that nothing's skewing your model to that way. But I will definitely ask one of my colleagues that might have some more information about that, and I'll get back to you as well. And if there's any questions that you have, please feel free to email me. My email is hbrook with an E at camo.com, and I'll be happy to answer any extras. So one of the questions here is, if NIR is used to study the particle size effects of pharmaceutical blends, is there any special consideration for the pretreatment? Okay, now that's an interesting point. So, we tend to think of scattering effects as noise, but sometimes they're not, and that's a perfect example of when it's not noise. It's actually part of the structure that you're interested in, right? So how particle size will change the slope of your spectra, like we showed, I believe. Let me pull up the right slide for you. Okay, so yeah, particle size, this is a very clear effective particle size that you're seeing, if that's something that you're actually wanting to model, I wouldn't remove those effects, right? Because you're basically destroying the information that you care about. So that is something that you have to take in consideration. You need to know when you go into your data analysis, what is the structure? So what is the information that you want to get out? And what's going to be your noise? And it's different for every analysis. I have a question of if I have temperature as a variable, should I center and scale the data? So it depends on what you're looking at. I need to know more about your data for that. If you're looking at a number of variables like, say, temperature and pressure and conductivity and viscosity, where things are on different scales, then yes, that's when you're going to center and scale your data. If you're looking at spectroscopic data, then I would say no, because the relations of one data point to another, they're correlated to each other. As one changes, others change, but they sort of change together. So the variation in how those change makes a difference. But when you have the process values, because they're on different scales, right? So in spectroscopic data, they're all on the same scale. It's just the variation that's changing. So that's a little different. So maybe if you send me an email, then I can answer your question a little better in that case. All right, I believe that's all we have time for today. Again, just please feel free to email me. I'll send a follow-up email for this so you have that as well. And thank you again for coming today. Have a great rest of your Wednesday.